Observations on sine and cosine trends. Welcome back, everyone. In our previous lesson, we worked on constructing a summary table that lists the specific trigonometric ratios for various key angles. Now, while having those exact numerical values memorized is incredibly important for solving your calculations quickly, simply memorizing numbers isn't enough for true mastery. To really understand trigonometry, we need to look at the bigger picture, the patterns hidden within those values. By observing these patterns, we gain a much deeper conceptual understanding of how these functions actually behave. So, in this session, we are going to move beyond just looking at individual numbers and instead analyze the overall trends of the sine and cosine functions. Specifically, we will be investigating how their values change as the angle increases from 0 degrees all the way up to 90 degrees. Analyzing the trend of \sin A. Now that we've established that we are looking for patterns rather than just memorizing numbers, let's dive into the actual data. Let's examine the values of sine A as the angle increases incrementally from 0 degrees to 90 degrees. If you look at our list, when it equals 0 degrees, sine 0 degrees is exactly 0. As we move to 30 degrees, sine 30 degrees is 1/2, which is 0.5. Moving up to 45 degrees, sine 45 degrees is 1 over the square root of 2, which is approximately 0.707. At 60 degrees, sine 60 degrees is the square root of 3 over 2, which is about 0.866. Finally, when we reach 90 degrees, sine 90 degrees reaches its peak at 1. Now, let's make an important observation from these numbers. As the value of the angle increases, you can see that the value of sine A also increases. It starts at a minimum value of 0 and climbs up to a maximum value of 1. In mathematical terms, we say that sine A increases monotonically as it moves from 0 degrees to 90 degrees. Keep this upward trend in mind, because in the next slide, we are going to see if cosine behaves in the exact same way. Analyzing the trend of \cos A. Now that we have seen how the sine function behaves, let's shift our focus and examine the values of cosine A for that same set of angles we just discussed. Take a look at the values here. When the angle A is 0 degrees, cosine 0 degrees is equal to 1. As we move to 30 degrees, cosine 30 degrees is the square root of 3 over 2, which is approximately 0.866. At 45 degrees, we have cosine 45 degrees, which is 1 over the square root of 2, or about 0.707. As the angle continues to grow to 60 degrees, cosine 60 degrees becomes 1/2, or 0.5. Finally, when we reach 90 degrees, cosine 90 degrees drops down to 0. If you look closely at this pattern, you'll notice a very important observation. Unlike the sine function we just studied, which was increasing, here, as the value of the angle increases, the value of cosine A actually decreases. It starts at its maximum value of 1 and steadily drops to a minimum of 0. In mathematical terms, we say that cosine decreases monotonically as the angle moves from 0 to 90 degrees. This inverse relationship is something we will see reflected clearly in our upcoming example involving a leaning ladder. Real-world conceptual example, the leaning ladder. Now, I know looking at those tables of numbers in the previous slides might feel a bit abstract, so let's bring this to life with a real-world visualization. Imagine you have a ladder of a fixed length. Think of this length as our hypotenuse. Now, imagine this ladder is leaning against a vertical wall. We will let A represent the angle that the ladder makes with the ground. Let's look at step 1 to understand the sine trend, specifically focusing on the height. Remember, the sine of angle A is the ratio of the height of the ladder on the wall, which is our opposite side, to the total length of the ladder, our hypotenuse. Picture this: if the ladder is lying completely flat on the ground, the angle A is 0 degrees. In this position, the height of the ladder on the wall is obviously 0. Now, as you start to push the base of the ladder closer toward the wall, the angle A begins to increase. As that angle grows, you'll notice the top of the ladder climbs higher and higher up the wall. Finally, if you push it until the ladder is perfectly vertical, the angle A reaches 90 degrees. At this point, the height on the wall is exactly equal to the full length of the ladder, making our ratio equal to 1. So, our conclusion for sine is clear. As the angle increases, the height, or the sine value, also increases. Now, let's move to step 2 to analyze the cosine trend, focusing on the distance from the wall. Here, the cosine of angle A represents the ratio of the distance from the wall to the base of the ladder. That's our adjacent side, relative to the length of the ladder. Let's go back to our starting point. If the ladder is lying flat on the ground at an angle of 0 degrees, the base of the ladder is as far away from the wall as it can possibly be, meaning the distance is equal to the full length of the ladder, so our ratio is 1. As we push the base of the ladder closer to the wall to increase our angle A, the distance between the base and the wall naturally gets smaller. When the ladder reaches a perfectly vertical position at 90 degrees, the base is touching the wall, so the distance is now 0. Therefore, we can conclude that as the angle increases, the base distance, or the cosine value, decreases. This physical movement perfectly mirrors the mathematical trends we observed in the tables earlier. Key takeaways. First, let's summarize the sine trend we discussed earlier. As the angle increases from 0 degrees to 90 degrees, the value of sine A also increases, moving from 0 up to 1. On the other hand, we have the cosine trend. As the angle increases from 0 degrees to 90 degrees, the value of cosine A does the exact opposite. It decreases, starting from 1 and dropping down to 0. Finally, I want you to notice a very beautiful and important pattern called the complementary relationship. If you look closely at our tables from the previous slides, you'll see that sine 30 degrees is exactly equal to cosine 60 degrees, and similarly, sine 60 degrees equals cosine 30 degrees. This happens because as the sine ratio increases, the cosine ratio decreases in a perfectly mirrored fashion. Keep this symmetry in mind, as it will be incredibly helpful when we move on to identifying common mistakes in the next slide. Now that we have looked at the specific numerical values and visualized the movement of the ladder, let's bring everything together with our key takeaways. Common mistakes. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even students who understand the patterns we've discussed can sometimes fall into these traps during exams, so let's be very careful here. First, watch out for confusing the trends. It is a very natural mistake to assume that because the angle is getting larger, every trigonometric ratio must also be getting larger. However, as we saw when analyzing the sine and cosine values earlier, they behave differently. While sine increases as the angle grows, cosine does exactly the opposite. It decreases. Always keep that distinction in mind. Second, be careful about assuming that these values can ever exceed 1. Remember our discussion about the right-angled triangle and the leaning ladder. The hypotenuse is always the longest side of the triangle. Because sine is the ratio of the opposite side over the hypotenuse, and cosine is the ratio of the adjacent side over the hypotenuse, these values can never be greater than 1. The numerator can never be larger than the denominator. Finally, a very common error is mixing up the starting and ending values at 0 and 90 degrees. You might find yourself accidentally stating that sine 0 degrees equals 1 or cosine 0 degrees equals 0. If you ever feel unsure, don't panic. Just refer back to the trends we studied in the previous slides. Just remember, sine starts at 0 and goes up, while cosine starts at 1 and goes down. If you keep these 3 points in mind, you'll have a much stronger grasp of these fundamental trigonometric behaviors.